Modern software teams build massive continuous deployment pipelines, simulating thousands of users and running endless automated test suites. Yet, despite this massive expenditure of compute power, unpredictable structural technical debt still makes it to production. The core issue lies in our reliance on dynamic testing. This methodology strictly depends on compiling the code, executing it, and simulating load or user inputs to see how the system reacts. Because dynamic testing occurs after the software is compiled and running, it can only isolate a failure, the symptomatic result of an underlying issue. You are catching the crash, not the structural weakness that caused it. The alternative is static testing. This is the process of bypassing execution entirely, evaluating the code and system architecture at rest through mathematical and logical analysis. By inspecting the raw artifacts, the blueprints, the requirements, and the uncompiled source code, static testing targets the root defect directly. You avoid waiting for a failure to surface during a test run because you are neutralizing the cause. This split screen highlights the coverage limits of the two methods. Dynamic execution is constrained by its test cases. It can only verify the specific, pre-programmed pathways a developer remembered to check. Static testing maps out the entire architectural blueprint globally, exposing dead ends and structural flaws that runtime environments might only hit once in a million iterations. True software quality requires moving beyond post-compilation execution. Securing the architecture mathematically and logically at the earliest stages of design is the actual engineering mechanism behind the concept of shift left. The earliest and most cost-effective stage of static testing happens before a single line of code is written. It targets the initial requirements and design architectures. Often, teams rely on ad hoc or passive reviews, where engineers simply read through dense documentation. Cognitive fatigue quickly sets in, causing reviewers to skim over contradictions and miss critical edge cases. To counter this, the ISTQB outlines a strict formal review process. This framework replaces chaotic, unstructured meetings with tightly defined roles, specifically designating an author, a moderator, and multiple reviewers. A crucial role of this formal framework is that managers must be excluded from the review meetings. This ensures psychological safety, keeping the focus strictly on evaluating the artifact itself, not the employee who created it. Within these formal reviews, teams employ perspective-based reading, or PBR, to specifically counter the limitations of passive reading. PBR forces reviewers to adopt specific roles, translating the text into secondary deliverables. It turns document review from an administrative hurdle into an active, constructive engineering exercise. Consider an e-commerce microservice designed to handle a composite payment module, where a single transaction mixes reward points and a credit card charge. A passive read of this system's requirement document might verify that both payment types are accepted, easily overlooking missing transactional rollback rules if one method fails. When we apply PBR and assign someone the developer perspective, that reviewer is forced to actively translate the text into a secondary work product, like an entity relationship diagram. By drawing the logic out, the reviewer immediately hits a roadblock, discovering a missing rule for which payment method to deduct first. Concurrently, another reviewer is assigned the tester perspective. They must draft a test case table from that exact same document. When they try to define the retry limit for failed payments, they realize the specification is blank. The inability to write the test case triggers a red error state in their expected results. Because each reviewer approaches the document with a distinct operational goal, the overlap in the defects they discover is mathematically minimized. By forcing the creation of these secondary artifacts, perspective-based reading drastically raises the overall defect coverage of the architecture. The flaws are caught and resolved before the project reaches the compiler. Once the architecture is verified and coding begins, static testing transitions from human reading to automated algorithmic evaluation, known as static code analysis. Static analyzers interpret source code as a mathematical control flow graph. This node graph maps out a basic execution path. It consists of nodes, which represent individual blocks of executable code, and edges, which are the decision pathways connecting those blocks. We quantify the complexity of this graph using McCabe's cyclomatic complexity formula. V of G equals the number of edges minus the number of nodes plus 2 times the number of connected components. In this simple IF statement, 5 edges and 5 nodes calculate out to a final complexity score of 2, meaning there are 2 independent execution paths. Engineering guidelines set strict thresholds for these scores. A score over 10 degrades the maintainability of a module. A score over 20 destroys its testability, driving up future costs. Mapping cyclomatic complexity mathematically justifies when a module must be refactored. Teams can identify and remove architectural technical debt based purely on structural thresholds, without needing to run a single dynamic test. Beyond the flow of execution control, static analyzers also trace the exact path of data moving through that structure, a process called data flow analysis. This horizontal timeline tracks a single data point through the strictly ordered 3-step atomic life cycle every variable must follow. It must be defined, used, and then killed or removed from memory. Complex branching and nested loops can disrupt this sequence, creating data flow anomalies that dynamic testing scenarios rarely trigger. The most dangerous is the UR anomaly, where a variable is used before it is defined. The program attempts to read from uninitialized or void memory, which guarantees a system-wide runtime crash if that specific pathway is ever executed. Other structural errors include the DU anomaly, define then kill, which wastes system memory by creating variables that are never referenced. There is also the DD anomaly, define then redefine, indicating that an entire block of intermediate logic has been skipped or overwritten. Advanced static tools combine this data flow tracking with taint analysis. By tracing a variable's entire lifecycle, they guarantee that a hard-coded password or encryption key is never inadvertently passed to a public logging module. Neutralizing these atomic data anomalies while the code is at rest is the only reliable way to mathematically guarantee data integrity against rare edge cases. Implementing perspective-based reading and rigorous static analysis requires engineering hours up front. To justify this time, teams must look at the macroeconomic realities of software delivery. The financial impact of bugs is measured through the cost of quality paradigm. This model splits expenses into the cost of preventing defects versus the cost of failing to catch them. The cost of quality curve plots static analysis as an early appraisal cost, a small, predictable investment. But if a defect escapes into production, an exponential spike on the far right represents the external failure cost, causing massive financial damage from crashes and breaches. This disparity is driven by the snowball effect. A single missed transactional requirement in the design phase multiplies in complexity, code dependency, and integration difficulty at every subsequent stage of the development lifecycle. Static testing acts as a mandatory risk hedging strategy that replaces uncontrolled high-stakes failure costs with predictable appraisal costs. To verify that this risk hedging strategy is actually working, quality assurance architects track specific operational metrics. The first is phase containment effectiveness, or PCE. This metric measures the exact percentage of defects that are successfully trapped and resolved within the specific phase they were introduced, before they can roll forward into the next stage of development. The macro metric for the entire pipeline's health is defect removal efficiency, or DRE. Industry standards dictate that a system must maintain a DRE of over 90% before it is cleared for release. Hitting that 90% threshold consistently is mathematically impossible if a team relies solely on dynamic, execution-based testing. By the time the code is running, too many structural flaws are already buried deep in the architecture. Executing a shift-left strategy involves applying mathematical graphs and active review frameworks to build an impenetrable structural shield before the code ever runs.